Hey Math Geeks, it's more systems of equations. Today we'll be talking about a second algebraic method for solving systems of equations. And this method is called elimination. And as the name implies, we are going to try to eliminate one of the variables so that we can solve for the other variable. Let's take a look. Here's our first system. Step 1 for solving by elimination says to rewrite the system so that the terms are lined up for addition. So our x terms are lined up and our y terms are lined up. And then on the other side of the equation, our constant terms are lined up. So we are ready to go and step 1 is complete. Step 2, now that we're lined up, says to multiply one equation by a factor to create the opposite coefficients in either the x or y terms. So let's take a look here. We have 3x and x, and we have 1y and negative 2y. And we want to multiply one of these equations so that when we add the two equations together, we will eliminate one of the variables. So this is one of those cases where we have a lot of choice. So you don't have to do it this way, but I always look for the variable, if there is one, that has no coefficient. And I noticed that the corresponding variable down here is a negative 2y. So when I add these two together, I want to get the y's to cancel out. How will I do that? Well, I can do that by having 2y in the first equation. So if I multiply that first equation by a factor of 2, I will get 6x plus 2y is equal to 4. All I've done is created another version of this first equation. If I were to graph both this first version of equation 1 and the second version, we would see that they're exactly the same line. So I haven't changed anything in my system. And now I'm going to write the second equation down again, minus 2y equals 10. And what you will notice is that now if I add these two together, I'm going to get 2y plus negative 2y. Those are going to become 0 and my y term will be canceled out. So let's do that. Let's add the two equations together and solve for the remaining variable. So 6x plus x is 7x. As I mentioned, my y terms are going to cancel out. And on the other side of the equation, I have my constants. 4 plus 10 is 14. If I continue solving, I can divide both sides by 7. And I'll get x is equal to 2. So we have step 3 accomplished. Let's take a look at step 4. It says to substitute the value from step 3, so that's x equals 2, into either of the original equations. Either of the original equations. Here's another place where we have some choice. And then we'll solve for the remaining variable. So I'm going to pick equation number 2 because I have an x term that has no coefficient, so I think it'll be a little bit easier. So wherever I see x in that second equation, I'm going to substitute a 2. So 2 minus 2y equals 10. And now I need to solve for y. So I'm going to subtract 2 from both sides to get y by itself. That leaves me with negative 2y equals 8. And now I'll divide both sides by negative 2. And I'm left with a positive 1y is equal to negative 4. Okay, so I have x equals 2 and I have y equals negative 4. So I have a tentative solution at the point 2, negative 4. Let's clean up some of this so that we can check our solution. Step 4 says to check the solution by substituting the solution into both of the original equations. Okay, so 3x plus y equals 2. And I'm going to substitute in my solution point, 2, negative 4, and make sure it solves the first equation. So I have 3 times my x value, 2, plus y, which is negative 4, equals 2. That gives me 6 plus negative 4 equals 2, or 2 equals 2. So my solution to negative 4 does solve the first equation. And let's check again that it solves the second equation. We have x minus 2y equals 10. So my solution my x value for my solution is 2, minus 2 times y. The y value of my solution is negative 4, and that equals 10. So 2 plus 8 equals 10, or 10 equals 10. So I've shown that my solution point 2, negative 4 also solves the second equation. So the solution solves the system. And this is what elimination looks like when we have one solution. Let's take a look at another type. Here we have an example of a system that will give us no solution. And let's see what that looks like when we solve by elimination. So step 1 again is going to be to rewrite the system so the terms are lined up for addition. Let's see. We do have our x's lined up and our y's lined up, as well as our constants. So step 1 is already accomplished for us. Step 2, multiply one of the equations by a factor to create opposite coefficients in either the x or y term. Sometimes this step is already done for us. In this case, it is not. I have some options here. One of those options is to multiply the first equation by 2. That's going to give me a 4x for my x term, and when I add these two together, that'll cancel out the x's because I have a negative 4x term here. So let's go ahead and do that. Let's make a multiple copy of our first equation by distributing this 2 to all of the terms. So that'll give us 4x plus 2y equals 12. And now we'll add that to our second equation, 4x minus 2y equals 5. Okay, so you notice that my x terms cancel out as I had intended, so that just becomes 0. But look at what else is happening. My y terms are also canceling out. 2y minus 2y is also 0. So on the left side of the equation I have 0, and on the right side of the equation I have 12 plus 5 is 17. This reminds me of when we were solving algebraically using the substitution method. When we came up with an untrue statement like this, our system had no solution. A system with no solution means that the system has two parallel lines. Those lines will never meet and therefore never share any points. So what we need to do to make sure that this has no solution is prove that by showing that these lines are in fact parallel. So we'll need to see what their slopes are. Let's get them both in slope-intercept form, starting with the first one, 2x plus y equals 6. So to solve for y, in order to get it in slope-intercept form, I'll subtract 2x from both sides. That gives me y equals negative 2x plus 6. Let's do the second equation. All right, that is negative 4x minus 2y equals 5. To solve for y, I'm going to add 4x to both sides. That gives me negative 2y equals 4x plus 5. And finally, divide both sides by negative 2. And that gives us y equals negative 2x minus 5 halves. So did we show that we have two parallel lines? Well, this is line 1 right here, and the slope of this line you can see is negative 2. And here's line 2 right here, and the slope of this line is also negative 2. So these lines are in fact parallel. They will not meet, and they will not share any points. So our system has no solution. Let's take a look at the steps again. When we did step number 3, add the two equations together and solve for the remaining variable, we came up with an untrue statement. So step 4, we're really not able to execute step 4, which says substitute the value from step 3 into either of the original equations, solving for the other variable. But we don't have an x equals or a y equals. We have a 0 equals 17. So we're not able to perform step 4, and we're not able to perform step 5. So our new step 4 for these special cases is when we get an untrue statement, we need to start thinking that we have no solution and that the lines are parallel. So we need to prove the lines are parallel. And we do that by putting both lines in slope-intercept form. And we'll check to see that the slopes are equal. Let's take a look at our final example. In example number 3, we're going to solve algebraically using elimination, starting with step 1. Rewrite the system so the terms are lined up for addition. Once again, everything's been lined up for me, so step 1 is accomplished. multiply one equation by a factor in order to create opposite coefficients in either the x or y terms. But in this case, it's not already done. I have a negative x and a 2x and a positive 5y and a negative 10y. So I'm going to have to multiply one of these equations, and it looks like the smarter one would be the first one. If I multiply this by 2, notice that will give me a negative 2x plus 10y equals negative 12. So I have a negative 2x that will cancel out nicely when added to this 2x. So let's rewrite the second equation right below. And now move on to step 3, which tells us to add the two equations together, which will eliminate one of our variables. Okay, so I have negative 2x and 2x, and that becomes 0. And I have positive 10y and negative 10y, and that's also 0. And that's equal to negative 12 plus positive 12, and that's also equal to 0. So what I have here, after I've added my equations together, is I have 0 equals 0. Unlike the previous example, when we had no solution and we came up with 0 equals 17, an untrue statement, in this case, we're coming up with 0 equals 0, and that's a true statement. Remember when we used the substitution method and we came up with a true statement like this? That was an indicator that we had infinitely many solutions, meaning we have a second copy of the same exact line lying right on top of itself. Therefore, they share every point and they share an infinite number of solutions. So, in order to double check, we are going to need to put both of these lines into slope-intercept form and verify that they are in fact the same line. So let's start with negative x plus 5y equals negative 6. Add x to both sides. We'll get 5y equals x minus 6. Divide both sides by 5. And we get y equals 1/5 x minus 6/5. Okay, let's try it with the second equation. 2x minus 10y equals 12. I'm going to subtract 2x from both sides. That leaves me with negative 10y equals negative 2x plus 12. Divide both sides by negative 10. It'll give me y equals 1/5 x minus 12/10. If I were to simplify that, I would have y equals 1/5 x minus 6/5. So comparing these two lines, I have the same slope, 1/5, and I have the same y-intercept, negative 6/5. So this is in fact the same line, lying right on top of itself. They share infinitely many solutions. Okay, going back to our steps, since we had no value to substitute into the other equation in step 4, we could not complete steps 4 or step 5. So our new step 4 is, if we have a true statement, if we come up with a true statement when solving algebraically, then we need to prove that they are the same line. We do that by putting both lines into slope-intercept form. All right, let's sum things up the same way we did for our substitution method. This is what the different types of systems look like. Remember, when we have intersecting lines, they share one point. And what the equations might look like, what we really care about is that the slopes are different. If we have two lines with different slopes, even just a little bit different, they will eventually intersect and share one point. When we solve these algebraically using either substitution or using the elimination method, we will get x equals some number and y equals some number so that we actually have a solution point. All right, the second type of parallel lines, we can see that they never meet and therefore they share no solutions. The slopes will be the same and the y-intercepts will be different in parallel lines. When we solved algebraically using substitution and elimination, it produced an untrue statement similar to these two. When we get an untrue statement, that is a big indicator that we should be checking at this point for parallel lines. So we should be coming back to this step and looking to see that the slopes are the same and that the y-intercepts are different. Finally, we have the same line or two coinciding lines, however you want to think about it. It's two lines lying right on top of each other and sharing every single point. So they share an infinite number of solutions. The slopes will be the same and the y-intercepts will be the same. You can see that in these two lines, same slope, same y-intercept. When we solve algebraically using substitution or elimination, we will come up with a true statement like 0 equals 0. And at that point, you should be double checking. You should be putting both lines back into slope-intercept form to verify that they have the same slope and the same y-intercept and they are the same line. So that's it. That sums up solving systems using the method of elimination. And we'll be doing some more practice in class. I will see you then.